And now, believe me, the trick we have learned about finding the highest power in the denominator surprisingly works even when we extend our function. And you hear my word here, we extend our function into the kind of function where not exactly rational function any longer, but still having some denominator. And so this time, let me take you into example 4. And you know what I mean immediately when I finish writing down my function here. So we're still going to evaluate, and the plan for example 4, I am still going to stay with positive infinity. I mean, we're letting x approaching positive infinity. And so the kind of problem we have, let me introduce our first problem here. How about cube roots? Okay, so cube root of x squared plus 1, and I am going to divide by x to the 4th plus, or maybe let's use minus 2 right here. My creativity keeps changing. So this function is not quite a rational function any longer, but what still remains here is that we're having a fraction. But the reason it's no longer a rational function is because the numerator here is no longer a polynomial, but it's actually a polynomial inside a root. So it's got more fancy thing involved, and we're still going to find limits as x approaching positive infinity. So how I introduced earlier about this kind of problem is that we can still surprisingly tackle right into the denominator, recognize the highest power, and then produce a similar thing, 1 over, so here it's x to the 4th. So now the plan here is I am going to produce 1 over x to the 4th. And so just like that, if we multiply 1 over x to the 4th to the denominator, we have to ensure we multiply 1 over x to the 4th to the numerator as well. Okay? And so now, let me tell you, the denominator this time is going to work a little bit easier because there's no root involved, so I can easily distribute this 1 over x to the 4th to each term here. So let's tackle down the denominator first in this time. So immediately the denominator becomes 1 as I distributed that 1 over x to the 4th to that, and then minus 2 over x to the 4th. So that's what we have there. Now, so the plan here is we want to find a way to somehow distribute this into each one of those two terms, but inside of the root. So here's the treatment. You got to treat things cautiously here. But if you want this 1 over x to the 4th to go inside the 4th, I mean the cube root here, then we have to raise this to the 12th power. I hope I don't have to go too far back with the algebra, so reveal your own algebra skill to find out why. But here's the thing, if I want to bring this inside of the cube root, then so this is how I have to do it. So this is how it can be done. Cube root is now an overall root right here expression, but 1 over x to the 12, that's what this expression becomes when it goes through a cube root and become inside. And now that 1 over x to the 12 is going to be multiplied with x squared plus 1. And of course, my limit operation remains the same here in each of the steps, because in the end I haven't done any limit work yet. X going to positive infinity. And so now, but we can start doing some algebra for that ugly looking expression inside of our cube root here. So into my other board, and how about let me also keep the other board on part of our current screen now. But so here, I would say that the expression inside the root now becomes after distributing this 1 over x to the 12 here, we are going to have, so it's a cube root over r, but now x over, 1 over x to the 10th plus 1 over x to the 12th. And that's how I distributed each of those terms. And so, and then in my denominator, 1 minus 2 over x to the 4th. And now, of course, I'm still just manipulating around with the algebra of my function. And so I haven't done anything with the limit at all. But now we are about ready to apply the limit laws here. All right, so provided that all limit laws hold, including the limit laws that work on roots here, that work with roots. And so now we are allowed to do the following. I'm now going to have in my numerator an overall root expression. And inside of my root, I can tear it down to one separate limit for x going to positive infinity of the function 1 over x to the 10th plus another limit 1 over x to the 12 as x to positive infinity and divided by, and in the denominator I'm looking at limit of 1 for x getting to positive infinity minus limit of 2 over x to the 4th as x is getting to positive infinity. All right, and so now each individual term here, including those being inside the cube root, is now ready for final work here. So cube root, I have 0 plus 0, and in my denominator I have 1 minus 0. So my overall answer now is going to be a 0. And so that's why we can apply the same trick, but I wouldn't say that trick about degrees and top is less than the degree of the denominator gives you a 0 limit. We don't see this as having a degree anymore. And so in that way, the trick I mentioned earlier, that's why I show the trick, because I feel like I should share with anyone anything I've learned. I learned any of these once, but whatever I feel dangerous for my learning and for your own learning, I decide to tell you that, stay away from, do not overuse the tricks, okay? All right, so let's now look into another example problem right here, and I'll continue to lead the way. So part B of our example 4. All right, so part B of example 4. So now let's look at how about square root of x squared plus 1 minus x, and finding the limit as x goes to infinity. And here I really have to emphasize again before we can move on any further. But if we immediately apply the limit laws here, this is what we're going to get right here. Consequently, after applying the limit laws immediately into this, we are going to end up into square root of something that grows to infinity minus this as we apply limit laws and infinity. And square root of an infinity is you can kind of think that it's still in the end grow to infinity. Why is that? Because square root function in general is, as we going to the right end point, it keeps rising up and rising up vertically. And so yes, square root of an infinity, you can now see that as infinity, but minus infinity. This answer is not really 0. So saying that this is equal 0, this is a serious flaw right here. So don't go that way. Or in other words, applying the limit laws immediately is not going to help in this problem. We need to do some algebra. The entire lecture I've been doing today is, like I said, heavily based on algebra. So you got to get your algebra going. Again, I constantly remind anyone, one of my calculus students about this. Okay, so let's get into the real work here. So I am going to now note right here in this problem that we have a difference between two terms, a difference of two terms, and one of the term has a square root. And so I believe you have seen this trick in some of my, throughout my examples in some of the earlier video lectures, and I am going to apply that that trick again. There's a difference. So now I am going to multiply with its conjugate. Okay, so meaning the conjugate means so x squared plus 1 minus x. Its conjugate now is going to be, well, square root of x squared plus 1 inside, but plus x. That's what conjugate means. So if we have a difference, then the conjugate is the sum of those two exact identical terms. But now, just like that, we've learned that in algebra, and we've seen that all over our previous examples. Anytime we multiply an expression out of nowhere into our current expression, we make sure we have to divide that same expression away. So that means I am going to divide this by the same conjugate. So square root of x squared plus 1 plus x being divided. So that means we have to pretend that our denominator here was a 1. And yes, it was a 1. It's not only just like a pretending thing, you know. But in the end, I was just simply manipulating with the algebra. So limit operation still being untouched there. I'm just leaving it there. So now, so in my next work, and allow me again to bring up the other board as part of our screen now, for anyone viewing this video to be able to see the previous step. But so from the previous step right here, then the product of these two conjugate quantities becomes, so remind yourself that a minus b multiplied in product with its conjugate, a plus b. See, same two terms, but conjugate in the sense that this is minus, this is plus. So that product produces the difference of two squares. Okay? And so in that way, and once again, please, I don't need to reveal anyone on the difference of two squares identity. There are tons of resources over the web that can remind you about those algebraic identities right there. So here we're looking at multiplying the two conjugates here from our previous steps in the numerator. We're looking at square root of x squared plus 1, but being squared, and then minus with x squared. See, now we have a difference of two squares, and one of our square has square root inside. In the denominator, things simply becomes x squared plus 1 inside the square root, plus with an additional x outside of the square root. And everything so far that I'm moving is completely in terms of the algebra, nothing done with the calculus. So in other words, I'm leaving my limit symbol remains the same here, hanging throughout the entire steps right there. Okay, but now let's continue to put in more algebra steps, and if at some point we will recognize how useful that is. So square is famous for canceling square root, and so that means the square here, and inside we have a square root. So now square root cancel with square leaves behind x squared plus 1, but yoo-hoo, no more squares, no more square root as well. And so now minus x squared away. These two are being ready for being canceled out in the next step here in the denominator. Square root of x squared plus 1 plus x, and here x going to positive infinity. Okay, and so let's cancel away that identical term x squared right there. And so now, and yes, in this example problem in particular, we have to bring in more algebra steps, but trust me, algebra is never a waste to learn. Anywhere you go in the world, you need algebra. So this is 1 over here square root of x squared plus 1 plus x. And now we are taking limit. And so at this point, we are about ready to apply the limit laws right here, the basic limit laws right here that we've learned much earlier in the quarter. So here I'm looking at limit of 1 in my numerator, x going to positive infinity in the denominator, eventually it will lead to limit of x squared inside the square root plus limit of 1. Okay, and then letting limits go to positive infinity and letting limits here go to positive infinity. And then in the denominator, it's still altogether plus another limit of x right here. Okay, it's x getting to positive infinity. And so now, well, each one of these will give you, well, that one is a positive infinity, that one is a 1, that one is a positive infinity. So now, once again, what I need everybody or anyone viewing the video to understand, again, I have to use that cheating way of writing again. Even though I don't like it too much, but at some point we're still going to have to use it. But make sure you understand that the correct way. So the numerator goes to a fixed constant. The limit of the numerator went to a fixed constant, but the denominator continuously grows to positive infinity overall. That's what divided by an infinity really meant. So that's why in the beginning, when I first introduced, I have to admit, eventually we have to use it. But I normally don't like to always overuse this kind of way of writing it. Okay, but now into the problem itself right here. Okay, then see, imagine, remind yourself about that cake scenario, one cake, but the number of people who want the cake keeps growing. And so in that way, each person in the end only have if we have that many people wants the cake, eventually everyone gets none. Okay, and that's what this overall value is. That's what that overall limit becomes. All right, so that's how we handle, and I hope example 4 showed how the same trick we've learned can be applied, and some special trick can be applied here as well. Okay, so having the algebra going is really something that I highly recommend anyone viewing this video. Before you start viewing any lecture, remind yourself to review some algebra. And then along the way, as you view any of these videos, feel free to pause the video and review your algebra until you understand how these steps are being taken. I will never be able to explain any of these steps without your own understanding of the algebra. So please allow me to leave the algebra review for you to take that on as your own responsibility, anyone viewing this video. And then any of these videos on calculus must be built on top of your previously understanding algebra. Okay, but now let's keep applying and do some more examples that gives anyone viewing this video more experience. So the entire example 3 and 4, we were all looking at limits to positive infinity, and I had my intention because I wanted anyone who is studying with me is to be able to work with these things cautiously. So let's learn formally how we can handle these limits to negative infinity. So now I'm going to call that example number 5 right here. So now we don't need to invent new functions here. The one we have used before, how about minus 3x cubed plus 1 minus 3x cubed plus 1 and divided by 4x cubed minus 2x plus 2. Okay, and let's find that limit as this time, as I promised. Let's find out how we can do something like this to limits to negative infinity. Or another way of understanding this is the left-hand behavior of our function, our rational function. Okay? So here's the thing. Allow me to show you not necessarily the fastest method, but the safest way, and we'll always guarantee your final proper answer right here. And it's the most, I believe, the most proper solution, the most proper technique right here. Notice that we're letting x approaching negative infinity. So letting x going to negative infinity is the same as why don't we treat x here equals some negative z variable. Okay? And then if we let x equal some negative z right here, then think about this problem can equivalently be the same as, so each x is substituted, as I said, substituted by a negative z. And so here minus 3 times negative z cubed plus 1. Okay? And 4 times negative z. So we substitute it with a new variable in there. And here this is cube minus 2 times negative z, okay, plus 1. But now, since we're stepping into an entirely brand new variable here, and our variable now is actually letting z go to positive infinity. So that's the trick right there. So this trick works and guarantees 100% of time we work. Any time that we're working with the kind of problem where we're approaching negative infinity, then easiest way to think is think about you substitute your variable x, your main variable here, with some negative expression, some minus expression, and then let the actual variable itself to grow to positive infinity, and that there is going to make work to fall back into the way how we have been learning in example 2, example 3 and example 4. Okay, so I need to erase this little part right here because I need more space to move on. But so this is how it works. Okay, minus z, but in cube power, in parentheses, cube meaning, and together with that negative signs, algebra again tells you that it's going to be a positive 3z cube plus 1 in the numerator. Okay, and in the denominator, see, here we're looking at negative 4z cubed plus 2z plus 1, and we're letting z as our new variable. And the end, whatever the answer we found, admittedly, we turned our problem into a completely brand new problem, but whatever the answer coming out from this problem will be exactly the same answer as our originally posted problem. So this is z going to positive infinity. Okay, and so now this thing here, remind yourself that we had that, see, this is now a rational expression. So I am going to apply that trick, and maybe this time allow me to go a little skippy here. My highest denominator in this rational expression is a z cubed. So I am going to multiply with 1 over z cubed in the denominator. And I'm going to multiply the same 1 over z cubed to the numerator. All right, and the rest, the following many steps here, I'm going to leave that for viewers. Go ahead and feel free to pause the video, okay, and get your steps worked through right there. So promise me, even though I'm just teaching in a video lecture, I have no way to control this, but anyone submitting your work to me, I'll be able to tell whether you have learned the solid work. But make sure you carry through all the algebra work. All right, so go ahead and get your own answer right here. And once you're resuming the video, I am going to just simply show my final answer. All right, so hopefully you're back and having your own steps right there to verify, to find out the actual limits right here. I have no way to see your work from being a in video instructor. But your final answer should agree to be minus 3 over 4. And this is your final answer for that. Okay, so the only trick I need to add on top, hopefully you are fluent with how I've done the previous example, the earlier example. And so now what I've done here, the only big trick here is I let our traditional x, our beginning x variable, but I'm going to substitute that by a negative expression. So nail that down for me. Okay. All right. So now let's work out with another example here. And you can see that I actually purposely brought up these past problems we've done, but considering the left endpoint. All right, so part B of the example. How about x squared plus 1 inside the square root minus x. And this time on this function, let's find the limit as x approaching negative infinity. All right, and so again, that same starting trick that will perfectly guarantee that it will always work. And but useful only when x is going to negative infinity. Okay, so got to keep things clear. Which situation to use which technique like that. All right, so remind yourself, I am going to let x. Let x be substituted by some variable negative z. Okay, and so that is now the same as this problem turns into limits problem. Okay, the square root here, x is substituted by minus z, so minus z all square plus 1. This minus x is substituted by minus z, so here I'm looking at plus z algebraically, and then this expression is our new function with a new variable, and now we are going to reproduce the problem as a limit problem where we're letting z approaching positive infinity. That's the argument like that. Okay, and so now limit of z go to positive infinity. Here we're looking at square root of z squared plus 1 plus z. Okay, and so once again, let's apply that trick about the conjugate, because what I see here is we have a square root term, so that conjugate is a good trick to apply in case we need to get rid of the square root symbol right here, square root sign there. So multiply with square root of z squared plus 1, but minus z this time. Okay, and then I am going to divide by square root of z squared plus 1 minus z. And then let's pretend that our beginning expression here had a 1 in the denominator. Okay. All right, so in my next step, and again, allow me to put part of the other screen, put the other board on our part of the screen here. But so in my next step, and I'm still just working around with the algebra. So here we're looking at z is approaching positive infinity, and our expression now becomes so z squared plus 1 in square root and being square minus z squared, and this is what we get. It's a difference of 2 squared by multiplying two conjugate expressions, and so now the denominator becomes now square root of z squared plus 1 minus z. And so the good usefulness now again in my next step, how about let me save some more space. So here in the numerator, again it's a huge yoo-hoo! No more square root here. Z squared plus 1 minus z squared. And then here we're looking at in the denominator square root of z squared plus 1 minus z. And this is limit as z going to positive infinity. Okay, so the example is going in at this point of this particular example problem. It is going in that direction pretty much the same as the example of example 4 part B. Like that, there was that square root. But at this point, let me stay really close with that technique we've learned previously. So, and then you will understand what I mean by what technique that is. So now, one more step, I'm canceling out that z squared term. So z going to positive infinity, and here we're looking at 1 over the square root of z squared plus 1 minus z. Okay, and so see what I mentioned earlier just now is that in the earlier example 4b, we had a quite similar problem, and we ended up with something similar to this with a plus here, and there I was able to explain in the concept of a 1 over the infinity. Feel free to roll back to that of this video to that earlier problem and to find out what I'm talking about. But like I said, personally for myself, I try to avoid that as much as I can. So anywhere I can actually avoid, and I'm not doing, then I'll just avoid. So here I'm not going to rushly say it's 1 over infinity. It's hard to see. That's the point. It's hard to see. So it's not easily seen why it's 1 over infinity for the bottom here. So let's really apply the limits. We've learned the thing about recognizing a high power. Okay, so here's a trick. The denominator here, the numerator of our expression here is just a constant, so no worry about that. The denominator here has some powers involved. Agree? Okay, and then each of these power here, so think about it. Now, the logic here is that this is a power 1, this is a power 2, but I'm not going to rushly say that this is a power 2 totally being the highest power in my denominator. Because notice, it's a power 2 but being inside of a square root. So think about it. Even though we're still being stuck with that 1 right here, but think about the numerically at the end, the z squared, but inside the square root will be somewhere near to just simply a z value. Square cancel with square root. So really the truthful highest power in the denominator is just degree 1, power 1. So that means now I am going to multiply 1 over z. Like I said, I recognize power 1 is the highest power in my denominator. Okay, so I'm doing that. All right, and so in my next step, numerator becomes a 1 over z, and denominator becomes so I'm starting to go skippy a little bit, but here we're looking at 1 over z squared. See, distributing this 1 over z to that first term and really further try to put that into the inside the square root, and 1 over z squared multiply with z squared plus 1. All of that inside the square root, and here minus 1. Okay, and we take limit as that's not x any longer. Z going to positive infinity. Okay, and so now, and again, as I said, at any point you feel like anyone viewing the video is feeling like you got lost, feel free to pause the video and really with papers and pencils work your steps out until you can actually agree with what I did right here, or throw me a comment on my video here on YouTube, or if you actually enroll in my class and be appointed to view these videos, feel free to message me and ask me how I can clarify these for you, or meet with me at my designated office hours. So now, inside of the square root, now if we're distributing that 1 over z squared expression, then we're looking at, so one more algebra step. So 1 over z in the numerator, but here in the denominator, square root 1 plus 1 over z squared minus 1. Taking the limit as z goes to positive infinity. And so now at this point, things are quite laid out for us right here. We can now say that this limit can be the same as it's a limit of that 1 over z, letting z go to positive infinity. In the denominator, eventually we're going to end up with square root of limit of 1 plus limit of 1 over z squared minus, outside of the square root here, we're going to subtract the limit of 1 again. Okay, and then all of these limits operations are going to positive infinity. Z goes to positive infinity. Okay. All right. And so now at this point, the answer is really around the corner. So our final answer, and let me erase a part of my work here, that much earlier part of my work, because it's been there long enough. All right, so now continuing with all that steps there. This time, let me bring up that other board on that where we came from, and so now numerator becomes a 0, straight or 0. Denominator inside the square root, we have square root of 1 plus 0, and then in the outside of that square root, but still in the denominator, minus 1. So in the end, this is a completely something that we can completely calculate, that we can entirely calculate. And so the answer overall is 0. All right, so now our final answer to this beginning problem was 0. That's what it is. And so now we're close, but still not quite all done in terms of seeing all limits problem at infinity. So let's consider some special ones. Let's consider the limits at infinity for some special function. And so here, how about I would say special ones. And special ones, I mean some finding limits at infinity for some special function. So the first one on my list here is e to the x. And this e to the x here, once we have found an answer to this limit, it also represents and so again, back into what I was saying earlier, that once we have found the answer to this particular e to the x function, then that answer can also be extended to the rest of the entire family of the exponential function. And so now I'm going to say we're going to consider the right-hand behavior of this function. And so now for these special ones, actually allow me to explain the final answer graphically by the graph. So at this point in your learning, I highly recommend be as flexible as you can. So I purposely, throughout all of my lectures, sometimes I use the table approach, sometimes I use the graphical approach, and sometimes I use algebraic techniques right there to find. So it's just whichever that's best for us to find the final answer here. We're gonna just have to bring it in and use that for our best purpose. So here's the graph of e to the x. So I'm going to return to my blank decimals, and e to the x has this famous shape right here. And then I can also bring it in put in some closer zoom. Okay, and so here's the graph for e to the x. And so what I can see here is that the problem that we're looking at is to find the limit as x is getting to positive infinity. And so in that way, now pretending that my mouse cursor is at somewhere, okay? Let's say my mouse cursor is somewhere, but now I'm tracing and keep getting further to the right-hand side. So my mouse cursor is going further to the right-hand side, and as I'm moving to the right-hand side, keep going further to the right-hand side, my tracing point keep rising higher and rising higher and rising higher. And so now we can make a final conclusion regarding our e to the x function, that this limit or the right-hand behavior of this e to the x function is a positive infinity. And just the graph is revealing its own truth. Like no need to argue about that. No one can argue about that. Okay? And so same function, e to the x, and the result we're about to find here is also going to be applicable to the rest of the entire family of a to the x function, exponential function. So e to the x is just one member among many other exponential function members. But this time, let's say, what about the left-hand behavior? So limit of e to the x as we're letting x going to negative infinity. Now, so you have seen that in the graph earlier, and let me quickly bring the graph back. But so here, our graph here this time, but if we keep looking at the graph, further back and further back to the left, further back to the left, meaning we're approaching negative infinity. And let me even drag that further to extend our view further to the negative side. And what do we see right here? The vertical height drop, keep dropping, but never hits that x-axis here. So now we can make a final conclusion that this is going to be limit 0. So as x is getting to negative infinity for e to the x, this function has limit going to 0. So these are the two special ones I want to introduce so far, but it's the it's the right and hand behaviors of our e to the x function. So e to the x function. And now what about our trig function? Trig functions for calculus students, for us, the calculus students, trig functions are among the quite familiar functions for us. So let me specifically bring up the two basic trig functions, sine and cosine of x. Sine of x and cosine of x. And so let me leave some space here. So after considering sine of x, then we're going to head into cosine of x. But what is the limit for sine of x as we're letting x approaching positive infinity? Positive infinity, or what is the right-hand behavior of this sine of x function? Okay, so once again, let's quickly find out, and then after we look at the graph right here for sine of x right here, then we should also, when I come back with this board right here, we should also be able to recognize the result for the left-hand behavior as well. So let's look at the graph one time to save yourself some time, and then we're gonna be able to make an estimate together, and one estimate for two problems. All right, so back on my Desmos again. Y equals sine of x. Okay, and so now maybe in this small limited window it's not telling much of a story. Let's zoom it out further, and let's zoom it out further. So now what's going on with the right-hand behavior and the left-hand behavior? Do we really have a behavior? The function itself basically just waving up, waving down, waving up, waving down further to the right hand. And then the function, as we're getting to the left hand, it's doing the similar thing, waving down, waving up, waving down, waving up and down infinitely. So at some point it hits the x-axis, but at some other point it hits 1, at some other point it hits negative 1. So it's doing that alternating nature, alternating or oscillating nature. And so now with this nature of our sine function in particular, coming back to my board here, and now I can say that the right hand point of this sine of x function, or the limits for this special function, how about let's stick with the term limits, limit of sine of x as x get into positive infinity. The answer here is does not exist, because it keeps bouncing up, bouncing down. At some point it can equals 1, some point it equals the negative 1, some other point it equals 0. So and the graph itself, as you have seen, it keeps bouncing up, bouncing down. So which value does it go to? It's not really go to any value, and it could even go to any value between negative 1 and 1. And so that right-hand behavior is a non-existing behavior. I mean, we don't really have a particular behavior for the right hand. It's just going up, going down like that. And so consequently, in the same way of explaining sine of x as we're approaching negative infinity, also consequently going to give a non-existing limit. So that's one thing to nail down, and treating that as among the special limits at infinity right here. And so let's look at cosine. So limits, and similar to sine of x, and anyone, before I pull up the graph, anyone can also predict what that answer is already. So cosine of x, I'm getting back to my graphing screen, and right now it's sine of x, but let me quickly change that to cosine. So cosine of x, another wave function. So it wave down, it wave up, wave down, it waves up. Same way as we navigating to the negative side, it keep waving down, waving up, waving down, waving up, and the further we go, it keep remain, no matter how far we go, it keep remaining that same nature right there, waving up, waving down. And so in that way, once again, back to our conclusion, does cosine of x function, as x is approaching positive infinity, the answer has to be a non-existing limit. And the same with cosine of x, as we're letting x approach negative infinity, that answer there is also a DNE. So these are a couple known ones, and so put it down in your pocket reference somewhere, so that at some point later on when we see any of these, you don't have to reinvent. You just simply say sine of x is limits to infinity, that's a DNE. Sine of x, limit of x go to negative infinity, it's a DNE. Okay. All right. And so now as we keep expanding our understanding for limits at infinity, then let's look at another class of special problem. And we're still looking at limits at infinity, but I put these problems I'm about to introduce in example 6 right here. And so let's evaluate again. And so these are just different limit problems I want to introduce. And we have seen just previously some limit at infinity for exponential function. So let's look at e to the x, how's that? Over 1 plus e to the 2x. Okay, limits, we're letting x going to positive infinity, for example. Okay, so now what I'm seeing here, again, don't do this. If we apply directly the limit laws, the numerator gives us an infinity, denominator gives us a 1 plus infinity, and in our easy enough way to understand, and 1 plus any infinity is an infinity. So the worst thing is someone is going to end up saying this is canceling out and get a 1. Maybe the answer is 1, but maybe it's something else. Bottom line, infinity divide infinity cannot be some value that we cancel things away. So this is a rush assumption. We will apply the limit laws, but at some steps after we have some algebraic treatments. So here's the thing. Let me open your point of view a little bit toward these kind of functions right here. But you see e to the 2x in the denominator, e to the 2x. Why don't we understand that? Why don't we understand that, see that as e to the x but being squared? Okay, so there's a reason why I'm doing that. So now after we take account on that, let's go back to our original problem. E to the x in the numerator. In the denominator I have a 1 plus e to the x, but square. That's what I pointed out earlier. But now if you observe the entire expression together, then we're going to be able to see that repetitive e to the x expression here. We got e to the x in the numerator and some other e to the x again with some other power here, and letting x go to positive infinity. So this is not really a formal term, but I developed this term on my own because this is how I see it. It looks just like the way this function behaves, this overall function, even though we got crazy e to the x all over, but it behaves similar to a rational function, because if we treat that e to the x in the numerator here as one huge x variable, and in the denominator we have another 1 plus x squared here, where the big X is the e to the x. So if we're looking at it this way, right, then it is just like a rational expression, a rational function. And that's why this kind of function, and trust me, as you work oftenly enough with these things, as you work often enough, you're going to get used to it. But so I refer to these as how about kind of like in my own term right here, rational like, because they behave, this function behaves like a rational function. And so how do we treat? And there's a reason why I pointed out how it looks like a rational, because we can apply that technique we've learned back in rational function into here. So now, if we remember, if we're looking at this, the e to the x is one big X, big capital X over 1 plus x squared, then polynomial here, polynomial in the denominator. Highest power in the denominator is power 2. And that's what I'm about to do. I am going to multiply the denominator by 1 over e to the x. This is my e to the 2x actually, okay, because that's my highest power in the denominator, the power of e to the x. And then if I multiply that to the denominator, then make sure, and it's the rule of algebra again, that we have to multiply this to the numerator. And so 1 over e to the 2x being multiplied there. And so now, and so the technique we're using here is also just like the technique we applied for the rational function back then. That's why, you know, I keep, you know, referring this to a lot of my students, generations of students, that these I call the rational like functions. So this one here, and we're still manipulating with the algebra, and it gives me, you see my numerator here, e to the x cancel with e to the 2x, gives me 1 over e to the x right here. All right, you don't need to rush to catch up, to get yourself caught up with my lecture here. Feel free to pause the video to find out why or how I came from e to the 2x, multiply with 1 over e to the 2x to get there. Okay, I mean, quickly maybe on scratch work, you can think about e to the 2x multiply with e to the x multiply with e to the 2x, but e to the 2x is e to the x times e to the x. How's that? Okay, and that explains. And then that will cancel and leave behind an 1 over e to the x. Okay, and so now the numerator together leaves 1 over e to the x. The denominator, as we're distributing this into the two terms in my denominator, first term becomes 1 over e to the 2x, and the next term here, e to the x, but all squared is the same, essentially the same as e to the 2x. So these two cancel. So we have a plus 1. Okay, and our limits problem becomes that. Okay, and so it's a pretty ugly looking expression, 1 over e to the x over 1 over e to the 2x plus 1. But then, but here we are ready to apply our limit laws, our basic limit laws right here. So this is the same as limit of 1 over e to the x, okay, and divided by the limit of 1 over e to the 2x, okay, plus the limit of the function 1 when x is approaching positive infinity. All right, and let's get to the other board. And also leave that first board there in part of our screen. And so now, notice for yourself, this limit 1 over e to the x right there is the same as, and by the way, letting x to negative infinity. Now, I meant positive infinity. Okay, so this particular one, now e 1 over e to the x is the same as e to the minus x. Or maybe a better way of understanding this is, you see, just observing this entire expression right here, we having a constant that's divided by something that's growing big and growing big and growing big. So the overall answer there has to be a 0. And so now we are ready for making that final conclusion. Thus, in the numerator, it becomes a 0. Okay? This other part right here, limit of 1 over e to the 2x as x getting to positive infinity, also gives me a 0 due to the fact that, you see, let me tear it down a little bit. Limit 1 over e to the 2x as x go to infinity. That is again the same as 1, but divided by something that keeps growing to infinity. And so that there would be a 0 and plus 1. So our overall answer now is actually a 0. All right. And so back to our final answers right here. For our final answer, concluded answer here, beginning e to the x over 1 plus e to the 2x. But final answer now is 0. Okay? And then the same function, e to the x over 1 plus e to the 2x, the same rational like. And of course, this is not the only rational like function that involves e to the x out there, but surprisingly, left hand and right hand behavior looks quite different. Actually, I shouldn't say quite different because I already knew the answer. So let's find out. Here I'm going to let x go to negative infinity. So I purposely stayed with the same function, but this time I'm going to consider the left hand behavior. This is part B. Okay? And so remember the trick we've had earlier, when x is going to negative infinity, the best way of doing that, the best practice of doing this is let's let x be substituted by negative z, and sort of like an external variable. And so now we're looking at e to the minus z divided by 1 plus e to the minus 2z. And this is now becoming a limit problem where we're letting z approach positive infinity. Okay? And so I am about to put in a lot of algebra steps after this. But, well, e to the minus z is the same as 1 over e to the z. And then in the denominator, I have 1 plus e to the minus 2z. So it's the same as 1 plus 1 over e to the 2z. Right? Letting z grows to positive infinity. But right here, actually, it seems like a lot of steps, and I accidentally, I mistakenly said putting in a lot of algebra, but right here, actually, if you're looking at this point, we recall from the part A that we've done previously, then this was one of the near the end step already. So this is how I argue it in my next step right here. Limit law says I can go limit of 1 over e to the z, okay, letting z go to positive infinity. The denominator becomes a limit of 1, letting z goes to positive infinity, plus limit of 1 over e to the 2z, okay, and z going to positive infinity. And so now each one of these, we have seen that in our earlier example, and the exact same argument is going to happen here again. This is going to be a 0 limit in the numerator. It's a limit 1 here for that, and it's a limit 0 right here for that. Was 0 here. So our overall answer is a 0. Okay, or making a final conclusion. Or maybe let me get back to the other board there. Then this limit is, after a lot of steps, is equal to 0 as well. So we found a left-hand behavior of the same function here. And this kind of function, I refer to that as rational like, because due to my explanation that I gave previously. All right, and in this last example of our current lecture here, example 7, and I only need to bring one problem, but to solve this problem, I will bring up something that we have learned previously, but only within our study of calculus here. But I'm sure you have learned that prior to this point. So let's evaluate again. That, how about cosine of x? Okay, but in product with e to the minus x right here. So e to the minus x in product with cosine of x. And now we want to find the limit as x approaches positive infinity. And that's just one problem right there. We don't need part A, B, and C. And you see what I mean right there. Okay, so a function like this, if we're simply looking at, if we're applying the limit law, immediately we're going to fail seriously, because cosine itself is a DNE. Okay, if we think about finding limits for e to the minus x, whatever that is, we're multiplying with the limits for cosine of x right here, x going to this. Well, this is a DNE, so we don't know what that answer is, so we can't multiply a DNE with some other limits right there. And so applying limit laws immediately is not going to work. And again, I remind anyone that there's a product right here. But so now here's something that we have learned before that will be again become handy here. The squeeze theorem. The squeeze theorem. So here's the thing. Cosine of x is famously known to be anywhere from -1 to 1. Okay? And if you need to remind yourself what the squeeze theorem is all about, go ahead and pause the video, roll back to the earlier lectures where I specifically taught about how to use a squeeze theorem to find a limit. Then go ahead and review that video and then come back to this. All right? But so assuming you already reviewed your squeeze theorem, and so cosine is famously known to be anywhere from -1 to 1. No one can argue about it. Okay? But now our function in the beginning here did not only have cosine of x. It had cosine of x and some additional in products with e to the negative x. And so I am going to multiply e to the negative x to cosine of x in my middle part of this three-sided inequality. But that means that e to the negative x must also be multiplied to the other two sides, trapping this expression in the middle. So now the far left there becomes a negative e to the minus x. And this is e to the minus x, positive e to the minus x. And so now this is how I see it. Squeeze theorem said, and this is our ultimate function that we're attempting to find limit. So this function is having some two known trapping functions outside of it. This is some g of x being always known below this, and this is some function h of x is also known to be always above this function of ours in the middle here. Further, what else do we know about these two trapping functions? So let me turn into the other board there. E to the minus x, this is h of x right here. But if we're finding that limit as x goes to positive infinity, then this is the same as 1 over e to the x. Taking limits as x go to positive infinity. And so this means we have a constant 1, but divide by something that keep growing to positive infinity, keep growing up bigger and growing up bigger. So I don't want anybody to think of that as divided by an infinity, but I want anyone to think of that as we have 1, but divided by an expression that keeps growing. And so that gives me an overall, the overall quotient here eventually becomes the limit 0. Okay? On the other hand, negative e to the minus x, this is our g function, our other trapping function below right here. As we're letting x to positive infinity, then this is the same algebraically as negative 1 over e to the x. letting x grow to positive infinity. So we can think of this as a negative 1 over infinity, and this is going to be a 0 as well. So the two trapping functions, the result here is, this is result number 2 right here, the two trapping functions meet the same limits when we are attempting this limits at infinity. And before that we came to, this is what we made, our first conclusion was that our function was trapped in between two other functions g and h right here. And so now we are ready to make that final conclusion, e to the minus x times, or in product with cosine of x. This function, if we're taking limits as x approaches positive infinity, the limit has to be 0. That's how useful squeeze theorem we learned a little while back then. It's still within our days learning calculus, but now it becomes useful again for limits at infinity. And so this final limit is 0. All right, and now we are at a final remark of this discussion in terms of limits at infinity. And so let's come up with a formal definition. A horizontal line, a line y equals L. Any horizontal line y equals L is called a horizontal asymptote. If, or I shouldn't say, it's a little too early to say that, horizontal asymptote of a function f of x if either the function, the limit of the function as x approaches positive infinity equals L, or in the other case around, the limit f of x as x approaches negative infinity equals L. So if either one of these cases happens, then we're saying that the horizontal line y equals L is the horizontal asymptote of the function f of x. Horizontal asymptote. Have we heard of that term before? Oh yes. I mean, long before we came to calculus here, we've seen horizontal asymptote. And so an asymptote in general is any line where an asymptote in general is any line where the graph will never cross through. Okay, and here particularly horizontal asymptote is a line where the graph will never cross through vertically. The line itself is a horizontal line, but vertically it won't cross through. So let me bring up some example we've had earlier. So this problem where we've had earlier, where it's e to the x and divided by 1 plus e to the 2x right here. We found the limit of this function. The limit as x going to positive infinity. Okay, and allow me to bring this into some closer zoom right here. Okay, so this function has, graphically looking, okay, looking at the graph here, then I can see that we have some horizontal asymptote nature going on here. Okay, the graph itself attempts to get close to that horizontal line, and that line here is y equals 0. So how does that agree with our work that we have done previously? Okay, so let's find out. But so we have proven in previous work and throughout example 6, I believe, that e to the x over 1 plus e to the 2x. This function has, if we consider, if we were, as we found that limits to be, as x approaches positive infinity, we found that our answer before was 0. So now, that's why it's consistent with what we've just now seen in the graph, that y equals 0 is the horizontal asymptote of this function. Okay? Or in some other function, in some other problem that we have done. Let's say, let's look at our function being, and how about let me turn this off, this function off, and look at some other function even before that. How about square root of x squared plus 1 and plus x. All right. So this function actually let me change this to minus x, because that was the one that we did in our example itself. Okay, so this function square root of x squared plus 1 minus x among our examples that we have already done. Okay. Then notice right now graphically, and before I turn the graph away, but notice if we're letting x approach positive infinity, then this function becomes asymptotic, horizontally asymptotic. Okay, so let me drag it back here, and as I said again, as we're tracing along the graph and keep moving further out and further out to the right-hand side, this blue graph of our function x squared plus 1 in square root minus x becomes asymptotic, horizontally asymptotic. So that is consistent with the fact that we have found in our earlier example question that this function we're looking at. All right. So square root of x squared plus 1 minus x here, and then as we were considering x approaching positive infinity, our answer was 0. So once again, it agrees with the graph that we saw. That's y, the line y equals 0, or namely the x-axis is the horizontal asymptote. And remind yourself from algebra, you didn't have to wait until calculus again to understand what a horizontal asymptote is. But horizontal asymptote, a lot of time being referred by the shorthand notation HA right here for horizontal asymptote. And so, and one more quick little demonstration here again. But let's, how about look at even some earlier example. Let me turn this one off right here. And let's bring up some other one. Let's look at some rational ones. So the rational we've had was, okay, in parentheses, minus 3 x cubed, how about x cubed, plus 1, okay, and divided by 4x cubed. Okay, and you're starting to see, before I completed my function here, you're starting to see horizontal asymptote right here. But wait until I actually finish. So horizontal asymptote. Now, I'm not saying that at some point, the real truth about horizontal asymptote is it's not exactly, it's not only asymptotic. At some point, it could cross. So it's not like entirely staying away from the horizontal asymptote, but eventually as so horizontal asymptote or horizontal asymptote in our calculus understanding, it refers to long and behaviors right here. So and behaviors in the long run right here. Then to the right and to the left, our function seems to approach. So recall for yourself that this function previously, when we were doing it, it was, let's say, what was it? The limit here was negative 3/4. So, all right, so that line in purple here, negative 3/4, maybe I should have put that in black line right there. Okay, negative 3/4 is the horizontal asymptote, because you see the graph did cross that, but then after a little while, then it's gonna only become asymptotic. And let me bring it in even in closer zoom right there. So for horizontal asymptote, it's going a little loose in the sense that it can still cross, but then eventually at an x value far enough, and it's gonna only get close and get close. Okay, and so back into our earlier actual calculus work, then we found out that that function I just had on my computer graphing screen right there, that was so minus 3x cubed plus 1, and we divided by 4x cubed minus 2x plus 2 right there. Okay, and actually plus 1. Okay, and this limit now going to the right end, it was negative 3/4. We also investigated negative 3x cubed plus 1, same function, over 4x cubed minus 2x plus 1, limits as x goes to positive infinity. This was also negative 3/4. And so that's the reason why, and according to the definition for horizontal asymptotes, then as long as we meet one of the two requirements, either the right end or the left end is going to a finite limits value, and I should have mentioned that back in my definition, but these are supposed to be finite value, okay, the value for L right there, and that's how we can have a horizontal line, okay. And so back to these examples, since we've seen all that here, that's why y equals the horizontal line, y equals negative 3/4 is being regarded as the horizontal asymptotes of this particular function.